Okay everybody, welcome back. Today we're finishing looking at the binomial probability distribution. Once again, remember for a binomial probability distribution we are looking at the same factors as we've had before. There must be two options, either success or failure. The probability of success must not change, and there are n independent trials. In this case, we're going to be finding the sample size, so it's a little bit different. We're focusing on finding out what the sample size is. In the past, we've been looking at finding out the value of x. This time, it's the value of n that we're considering. Now, this is heavily based on the CAS calculator, so we're going to go through a couple of examples. Okay, now for this first one here, we have a biased coin. It's found to have the probability of 0.3 of turning up heads. So that means that our p value in this case is 0.3, and it's found that the probability of getting at least one head, so of x being greater than or equal to 1, is 0.9424, and we're trying to figure out what n is equal to. Now I'm going to show you a couple of ways that we can work this out depending on whether we're doing this tech-free or tech-active. So let's go with the tech-free option first. Either way, we should first start by defining what x actually is. So we can let x equal the number of heads. Okay, that's what we're looking at. And from there, what we get is the expression that we've got up there. We're wanting to find the probability that x is greater than or equal to 1. At least 1 means 1 or more, 1, 2, 3, 4, and so on, that this equals to 0.9424. If we had to do this in a tech-free situation, which I will tell you is very, very unlikely, but this is the full working out that you can fill in your booklet. Probability x greater than or equal to 1, that is the same as doing 1 minus the probability that x equals 0. Okay, because greater or equal to 1 is every value except 0. And this equals 0.9424. We can then subtract 1 from each side and take our negative over as well, to give us 0.0576. To work out the probability that x equals 0, if we're doing this in tech-free, we've got to set up our binomial distribution ourselves. The start bit was n, choose x. N, we don't know our sample size. Our x value is 0. And then we're going, gosh, doesn't like n, does it? There we go. Okay, then we're going to have our probability of success, 0.3 to the power of how many of x, our x value is 0. Our q, our probability of failure, is 0.7, and how many times is that going to occur? It would be n times, however many times I do the trial. Remember, this power is usually n minus x, and x is 0. So as we keep solving this here, n choose 0. How many ways can we choose 0 objects? From n objects, there is only one way to choose 0. We simply choose 0. 0.3 to the power of 0 equals 0, times we have 0.7 to the power of n. Now, if we are trying to solve this, we know that what we do is we can take log of base 0.7 of each side. So we can turn this into a log equation. Log 0.7 we write as a subscript of 0.0576. And if we were doing this in tech-free, that would actually be the best we could do. That would be our answer. Nobody would expect you to be able to work this out by hand. Let's, for interest's sake though, pop this into the calculator and see what we would get. 0.7 of 0.0576. And we get an answer of close enough to 8. N equals 8. So therefore, how many times has the coin been tossed so that we're getting this probability? Our final answer would be 8. Now, if we're going to need to put this into our calculator anyway, there is an easier way of doing it. Also, hopefully you can see that if we didn't have a nice expression like 1 minus probability of 0 here, this could get very messy and very difficult to do by hand. Imagine if we had lots of these expressions here for the binomial for a whole lot of different values of x. Not going to be very nice and easy to work out. So let's look at how we'll do this in CAS and what it's expected to write in the exam. So if you got this question in an exam or a SAC, what I would expect you to do is to first of all, like we did before, define the variable. This is really important that you do. Number of heads, okay? Then what we do is we show the examiners, the assessors, that we know that x is binomial and we know that our value of n, that we don't know what it is, so we will leave it as n, and that we know the value of p is 0.3. We then set up the equation we want to solve. It is found the probability of getting at least one head, so that x is greater than or equal to 1 is equal to 0.9424. And now, this is where we do it in our calculator instead of this method here. Because we're looking at a range of values here, not just one value, it's going to be cumulative, we're going to need to use binomial CDF. There's two ways to find this. If you're just in the interactive menu, sometimes this is easier because we can find distribution, discrete, binomial, CDF. Our lowest value, our smallest value is this value here, 1. Let's leave our upper value for a minute. Our number of trials, this is what we're trying to find out, so I'm just going to call it x. Don't know why it's a capital, but we're just going to find it x. Our probability of success is 0.3. Our upper value, if we have x trials, however many that might be, say x was 10, say we were doing 10 trials, the upper value, the biggest value of x we could have is 10. If I was doing 20 trials, the biggest possible value of x would be 20. Because I'm doing x trials, the biggest possible value I can have is x. So we press OK. Now it does say wrong argument type. Don't worry about that. What we're going to do is just to highlight what's written here, and we're going to copy it. And what we need to do is to go into our graphs and tabs menu. I'll clear out this, and I'm going to get my keyboard up. Sorry, excuse me, I've lost my keyboard bit. There it is. Get my keyboard part. I'm going to paste this. Okay, so I've pasted this in and press execute. Now, if you didn't want to do it this way, the other way we could do it is to go to Catalogue, find our binomial CDF just here. If we are doing it that way, what you need to remember is the order that you type things in. So binomial CDF, what we get is our lower value first, then our upper, then our n, then our p. So just make sure if you put it into your calculator, you type it correctly. Notice this is calculator syntax. I never ever write this in my exam notation. Examiners do not like calculator syntax. This is the only notation we need. This here in red, this is for your own reference to figure out what you need to do. What we do then is that we get our table up. So we click on this little table button here, and it's going to give us a whole range of values. So if you need to change them, like I mentioned before, we've got this little button here, and that allows us to change our start and our end if we need. Our step should be 1 because we're dealing with our discrete probability. And now we look through here. These are our values of x. The y values represent the probabilities. I'm going to have a look for where it is equal to 0.9424, which is just here at an x value of 8. So therefore, I get my final value, as we worked out before, is n equals 8. What I've written in green is exactly the working out you should do in a SAC or an exam, okay? Yellow is how to do it by hand, but I highly, highly doubt you'll need to do it by hand, ever. Red is the calculator syntax for your own use, but you do not write it for the examiners. Okay, let's do one more example. So in our second one here, and I will point out this probability written here, 25%, that is different to what's in your booklet. I'm sorry for that. Can you please change your booklet so that it says 25%? Now this time I'm not going to try to do it by hand. We're just going to work out our exam notation. Because I've already defined x earlier, I'm going to use a different variable this time. So within the one assessment task or the one question, we should never use x twice, we should use different variables. So this time I'm going to let y equal, what we're looking at here is the number of times you must play the game to ensure the probability of winning. So number of wins is what we're concerned about here. We know it's binomial because we have two options. We can either win or not win, lose in the other way. So this is success and this is failure. The probability of winning a particular game is 0.42. So our probability of success does not change. We're looking at the number of times something occurs and we don't care about the order, so we know it's binomial. So we set up our distribution y is binomial. We write our n value first, which is n. This is what we're trying to find out. Our p-value is 0.42. Then we set up our equation. We want to find the probability that y, what is the fewest number of times you must play the game to ensure the probability of winning at least 3 times. Okay, so at least 3 times. Y is greater than or equal to 3, is more than 25%, which we can write as 0.25. So we go to our calculator here. Now notice if we had y is equal to 3, I would use binomial PDF. Because it's y greater than or equal to 3, I'm using binomial CDF. We can either type it straight in, or if you're worried like me sometimes that you might forget, we go to the main. I'll get rid of this one here. No. Okay, get rid of that one there. We're going to click, like we've done before, interactive, distribution, discrete, binomial CDF. Our lowest value this time is 3. Our upper value is x because it's going to be however many trials we do. Our number of trials is x. Our probability of success is 0.42. Now again, it's going to tell us error, wrong argument. That's okay. What we want to do is to copy this. And sorry about this a second, I'm just having trouble getting my keyboard. There we go. I'm wanting to copy it, and I'm wanting to go to the graphs and tabs menu again. So what I'm going to do is that I'm going to get my keyboard up again, which I keep losing. Sorry, I've got to move it around a little. I'm going to paste, execute, and now once again I click the table menu. Now where is it first greater than 3? We've got these errors. That makes sense. When x equals 0, we're never going to be getting a probability. We're wanting to know, remember these are our probabilities. For y to equal 0, that's not an option. That's not something we've been given here. So these values are not relevant in this case, because the smallest value we can have is y equals 3. Where is it bigger than 25% for the first time? So having a look here, for the first time at 4, it was 0.20. That's not at 20% here. But at 5, 0.35. This is the fewest, the smallest number of games to make sure the probability of winning is at least 3 times is more than 25%. So I need the first time my percentage here is above 25%. So my final answer, therefore, is that n equals 5. And this is exactly the working out we would show. Keep in mind, binomial CDF, if we're doing a range of values here, if within the probability I have it equal to one value, we'd use binomial PDF, our probability distribution function. Okay, everybody, that is it. We are done for today. Thank you very much. Any questions, please make sure you ask me next time.